So this will be the first part where you'll see some of the components in Rosetta. So far we've been talking about tools and some basic C++. We sort of have a chicken and egg problem where we can tell you about Rosetta, but we want you to play with it and explore it. So this is going to be just a real short intro to just the basics that you barely need in order to write an application to actually do some C++ coding, get compiling, and get into the cycle of writing some code. So we'll just try to go through it relatively quickly, but please ask questions if you want more details on things. So the task for this tutorial is going to be create an application that's going to print the score of for a structure that you pass in. How do I do this? So the inputs will be one or more structures as PDBs, and we're going to use the job distributor, which I'll tell you about in a bit, to get the structures in. So you won't have to worry about reading structures in any sort. And then we'll pass in the score function in. It'll be initialized through the command line parameters. So what your code will end up with is a pose and a score function. And from that, you should print the score of the pose. And if you pass in more than one structure, then you'll end up with a table where you'll have the structure tag and the total score. So if you pass in a different score function, you'll get out a different total score. So it will have a little bit of functionality to it. OK, so in order to do this, I'm going to tell you about some of the core modules that is used almost every time you want to make some application or something in Rosetta. It's a pose, a score function, and in order to do this, we're going to work with movers and the job distributor. I'm going to tell you just a little bit about movers and a little bit about the job distributor, but we're going to have lectures later in the week where we're going to get into more details about how the movers should be used in different ways that they can be in the job distributor as well. OK, so a pose is a representation for a molecule. It's a specific conformation, so it has all of the atom coordinates in space is the information that it keeps track of. It organizes this information associated with each atom. It has chemical information, so what type of residue or what type of functional group it's in. And the way that this is organized is through residue types. And so there's this concept of a residue as a collection of atoms. The idea comes from the positions along a sequence of a protein. So residue would be like the amino acid. But residue is generalized for nucleic acids and other polymers that don't necessarily have the idea of amino acid. And then to do branched polymers, they're organized in usually linear, but they can be a tree-like structure. And if there's loops, then those are modeled in another way. But for now, you can think of a pose as being a set of residues, and each residue has atomic coordinates with some chemical information associated with it. Also, the pose keeps track of energies that it caches for the score function, but that's handled behind the scenes, so you don't have to worry about that for now. But perhaps when you dig into it more, you'll see that is important. So the way this is organized is at a high level, we have a set of owning pointers to residues, which is a private member variable of a conformation, which is stored inside of the pose. And so each residue has a residue type, which is a constant reference to a residue type object. It has a vector of which are reals, which are the main chain torsions. So this is generally just 2 or 3. And then it has a vector of reals of the side chain conformation. So this will be 1, 2, 3, or 0 for proteins, for instance. And then it has which sequence position it's at and the chain, which can be useful in certain contexts. To organize the residues, they're organized into this thing called a fold tree. I'm not going to tell you too much about it now, but we are going to talk about it extensively later in the week. But the basic idea is that this measure keeps track of the connections between the residues. So there's peptides, chemical bonds, and jumps, and it says what the start and stop atoms are. And then if it's a jump, it has to say in space, how are these translated? So if you have, say, 2 structures that are docked together, then they would have a jump between them. Otherwise, they would have peptide connections that are connecting them. a key part of how the atom information or the coordinates are stored in space is rather than simply storing the Cartesian coordinate of each atom, the standard way of representing the coordinates is through these internal coordinates. And so this is where you have the torsion angles of the backbones and side chains. And since for each residue type it has a fixed bond lengths and angles, you can figure out through a recursive function where the atoms are in space. So to do that conversion between internal coordinates and Cartesian coordinates, there's this atom tree representation. And so this is kept in sync with whenever there's a change to the torsion angles, it's done lazily, and so that way you could ask for the actual atomic coordinates and it can go and figure out where it is. So this presents an interface where you can see the Cartesian coordinates, which are then sort of wrapped up into the conformation. But it gives a way of treating it both like Cartesian and like internal coordinates to the user. So this is another presentation of the interface.
Is there any overhead if you try to use the Cartesian coordinates?
Yeah, so people have found that Cartesian coordinates are actually good for certain types of sampling protocols. Mm-hmm. And so there's, in order to represent the Cartesian coordinates of the atoms for sampling, you can sort of go backwards and store the Cartesian coordinates as primary. It takes a bit more space because you now have more degrees of freedom, but for certain applications, it seems to work better.
No, sorry, that was not my actual question.
Oh, I'm sorry.
Is, I think that everything is stored in the folding tree, right? So when you go to when you try to make some operations with the Cartesian coordinates, is there any overhead doing that? It will cost more computation. It would need to translate from the folding tree to the Cartesian coordinates or not?
Yeah. So
we'll talk about this extensively, I believe, tomorrow.
Yeah. So hang on to this question, and I think it'll be more clear when we get into the details of this. But right. So for the outside, you don't really need to know about these details. What's important is that that there's these residues and they have properties to them. We're not even really going to get into the residues so much today. I just wanted to, give you an overview of what a pose is and sort of conceptually what it represents. Okay, so for the purposes of this tutorial, a score function conceptually is a sum of weighted score terms. So this is sort of the mathematical representation where each term has a weight, and this is the term I. So you have a particular conformation, and the term can go through and score the whole structure, and then it's multiplied by the weight and summed up. So that's what the total score is. So if you wanted to score a pose, you define a score function, for instance, and then if you wanted to change the parameters, perhaps you would do that. But then if you wanted to score it, there's a function called score, where you would pass it in a pose, and it would return a real score. So, yes?
What are the W and T?
W is they're real numbers that are weights, and T's are the score terms. So great segue, thanks. Okay, so energy terms, although it's not essential for this right now, it's good to get a sense of the sort of what types of score terms are available. And certain algorithms can be done more efficiently depending on what the score term is actually scoring. So a one-body term is just looking at a single residue. A two-body term is looking at just two residues together. And then there's two-body long range, which don't necessarily need to be close together in space. And then there's one-body, two-body, and two-body long range that have context around them. So depending on what type of energy method it is, it tells it when the score term needs to be updated as the conformation is changing. And then there's whole structure scores that can be, they can look at all the different residues. So in general, if you're writing a score term, you would want to find the simplest, smallest version of it, so that way it can be updated and most efficiently as possible. So just to give you some examples of score terms that fit into these different types, the Ramachandran term just looks at the backbone phi-psi angles, and the FA done is the Dunbrack term, which just looks at the side chain conformation. It may be backbone dependent as well. So these are just one-body terms because they just look at the conformation of a single residue. Two-body terms are like the FA attraction, FA repulsion, the FA solvation, and say the Hakelek, which if you know the conformation of two residues, then you can evaluate a particular instance of this score term, and then you would sum up over all pairs that are within some distance of each other in the structure. And then the two-body long range. These, in order to do the two-body, it builds first finds all of the pairs that are close together, and then evaluates the two-body term. The two-body long range does it the other way around. It first it asks the energy term which pairs are interacting, and then it finds them. So there's the Poisson-Boltzmann electrostatics, and then the electron density score term, for instance, fit into this criteria.
So is it looking at the atom tree when it's doing this, or the tree?
So are the score terms looking at that?
Yeah.
So they get an instance of the so different score terms do it differently, but they get representation in terms of the pose and then the residue conformations. And, so not directly through the atom. I mean, sometimes they get the information through the atom tree, but not directly. Sorry, the context dependent. So if this particularly depends on if it's in the environment, like exposed to solvent or not exposed to solvent. So like, for instance, the hydrogen bond term, there's a weighting where it's down-weighted to a fifth of the strength when it's exposed to solvent, for instance. But this is one-body, two-body, and long range as well. And then for whole structure terms, this is the radius of gyration, which is how expanded out the structure is. PAC-STAT, which looks at holes throughout the structure. RDC constraints, and so on. So a score function, an energy map is a fixed length vector where the parameters are score types. So there's an enum of score types that are defined, and each energy method is responsible for a certain set of score types. So the hydrogen bond, for instance, has a few score types associated with it, and it has different slots in the energy map. So this is like a n-dimensional vector, and the weights are going to be an n-dimensional vector, and to score it, you take the dot product between the two n-dimensional vectors. So there's an energy map that has a set of weights that are going to be non-zero, and those are the score terms that are going to be evaluated. So if an energy method, all of its score terms are 0, then when you go to score it, it doesn't have to evaluate the code at all. So to turn it off, you just set the weight of a score term to 0. And then there's energy method options, which if the parameters for the energy terms can be adjusted, then these are where they end up. So these are going to be set from the command line if they're set at all, so you don't have to really worry about that. And the weights file, I'll show you how to pass those in from the command line too, which will be part of the exercise. Any questions? Okay. So the mover, a mover is an abstraction for something that takes it a pose and applies something to the pose. So the classic example is the set torsion mover. So here you take a pose, you give it a specific residue at a specific angle, and you set the value of that torsion angle. So it just takes a whole structure and torques it around by one torsion angle. But this concept of a mover has been more generalized to basically like a protocol. So a mover can call other movers, which can call other movers. And so it turns into sort of a generic language of writing protocols. And so later we'll look at how this fits into the Rosetta scripts framework for allowing people to write protocols in XML format. But just as an example, there's an if mover, which evaluates something to be true or false, and then evaluates one mover if it's true and another mover if it's false. So this, you can sort of see how these different movers can be combined up into sort of arbitrarily complex protocols. Okay, so just say a little bit more about this. So mover is going to be a base class, and what you're going to do is write a class that derives from mover that's going to implement the apply function. So it will take in a pose reference and then do something to it. And since it's a mover, there's a bunch of components in Rosetta that know how to handle movers, and you can hand your class to that framework, in particular the job distributor, and it will apply the mover for you. So as far as this part is concerned, you can think of a mover as a class that implements an apply function. And it has some other initialization information, which will come up later, I guess tonight, right? Okay, so just a little bit about the job distributor. This is a general framework for getting structures into Rosetta and managing resources on computational cluster. So it has a variety of input and output formats that it recognizes, such as PDB files. Silent files are Rosetta specific and they're relatively compressed. They can read and write structures from relational databases. There's a whole lecture on job distributor and later, but I just wanted to give you a brief overview of it now, so that way you can won't get lost. So the way that the job distributor works is that you hand a mover to the run protocol, and if it has a cluster, it passes the mover and all the different structures to the different resources on the cluster, and it does what it wants, and then it returns the structures and prints them out at the end.
It doesn't handle multi-threading, right?
So distinguish between MPI parallelization and multi-threading. Multi-threading is on a single computer. There's sort of one instance of the program, and it's using it can run stuff in parallel within the instance of the application. MPI parallelization is where you have basically separate instances that are separate command lines that are running, but they can talk together because of using the MPI protocol. So MPI clusters are pretty common at sort of large-scale clusters that you would run it on, and it does do simple parallelization on MPI clusters, right. But Rosetta is not thread safe, so it's not doing multi-threaded running of movers. Okay, so if you wanted to use the job distributor, this is how you would do it. You would define an instance of a mover. This is a base class, but perhaps you would it would be your derived class that you would have. You would get an instance of the job distributor. So in this case, this is a function of the job distributor class, and it's called a static function, which means that you don't have to have an instance of the class in order to call the function. It's called getInstance, and what it does is returns a pointer to the instance of the job distributor. The reason why it's done this sort of convoluted way is that there really is only one job distributor throughout all of Rosetta. So it's created when it's necessary for the first time of getInstance, and then every other getInstance you'll get the same object back. So there's sort of a global data of one job distributor, and you can get access to it. So if you call this JD2, this is now a pointer to an instance of the job distributor. So just to note that this is going to be a raw pointer to the job distributor, because as Andrew was talking about smart pointers, when smart pointers go out of scope, if they're the last pointer to the object, then the object's destroyed. So if we put this into a smart pointer, then we would end up destroying our one version of the job distributor. So if we just get a raw pointer to it, then it lives on, and it will just be this global job distributor, and that's just the way that this is set up. So once you have the job distributor, you call the go function on it, and you pass in the instance of the mover, and it takes it from there and applies the mover to all the structures on the inputs. Does that make sense? Okay, so the task is going to be create a mover that takes in a pose in the apply function and is going to print this square row. In the tutorial, there's a more description about exactly how this should work. But the basic idea is that you pass this mover to the job distributor, and then it runs. So it should be pretty straightforward. The challenging part will be working in a branch, checking it out, compiling, getting it to run, looking at the output, and just basically navigating the code base and trying to make this work. So the logic, this is the easy part, but hopefully it'll be like a template, which then if you want to write further applications, you can go on from there. Some things you'll encounter that are not particularly anyway, so that you may see this as you're going through this. So this is a forward header. The idea of a header versus a CC file is that the header presents the interface to the user of your class. So if you just get the header, you get the signature for the class and other things associated with it. Sometimes even that is too much. All you need to know about is that a particular class exists. So this is where forward headers come in. This is basically all that should be contained in a forward header. Let me just go through the parts of this because you'll see this in the code, and it'd be worth explaining at least once. So when you include a file with an include statement, conceptually what's going on is that you've taken the contents of this file and copied and pasted it where this include is. What this means is that if this is put here and then say another class drives another file from it, and there's another, it includes the file where this is included, then the header would get instantiated multiple times. So you would get, if say there's, it ends up calling, it ends up, if there's global data or if there's other things in the file that should only be instantiated once, it gets called multiple times. So to prevent this, there are called include guards, and it's what the pattern is that you say if def. So this is a preprocessor macro. It says if this string or this identifier is defined, or if it's not defined, then make this block of code, put it in, and let C++ read it. This happens before the compiler gets the handle on it. It's called like a preprocessor. So it does all the preprocessors first before it starts looking at the code. And the first thing it does is it defines this definition, or this identifier. So that way the next time it goes through this, it says, is this defined? And it goes, yes, it is, and then it only does it once. OK, so what the forward header should do is it should do just the name of the class in a class, and this just lets anything that includes the forward header know that there is a thing called this class, and it's a valid name. So in some cases, if you just have an argument to a function, you may not need to know what the function actually does or what the class actually does. You just have to know that there's a class with that name. And then, as Andrew mentioned, this is the template or the type def for the owning pointer. This is an example of the atom pair features, just as an example. So this says that the OP, the owning pointer, the smart pointer, is a type def. So it says instead of this, you're allowed to use this this name here. So I think we're talking about template parameters later in the week as well. But in any sense, you can think of this as a magic incantation that you should do in a forward header if you're going to write a class. For this simple tutorial, you won't necessarily need to do this, but you'll encounter forward headers, and if you start making classes in Rosetta, then you'll have to make forward headers for them. Okay, and also might as well mention this. The namespaces, these are defined within the namespace. So in this case, it's protocols features, and the namespaces correspond to the directory structure. And this just allows, if you have different names and different namespaces, they won't collide. So it gives you some peace of mind that if you define a name of like my int, that it won't collide with Andrew's int if they're in different namespaces. And to keep the namespacing in the code separate or straightforward, we just keep the namespaces consistent with the file directory structure. So here, protocols, features, and this is the file name. This is the namespaces that would be associated with protocols and features. OK. One or two more things, and then I'll let you dive into it. One is the tracers. So rather than using cout or cerr through the standard template library, we have they're called tracers, and this is what we use for logging in Rosetta. They behave pretty much like you would expect stream operators to like cout to work, except we have more control over whether or not they're going to actually be put to the screen, and they have an additional tag in the beginning to show where it came from. So for instance, if you wanted to do this in your program, which you'll have to do, you will include basic tracer.hh, and this is a file in the basic directory called tracer.hh. And then towards the top of your header, in the CC file, not in the header, you would define a static tr tracer with the constructor takes in a string which tells you which class this is for. So this is the one for pose. It's in core./pose/pose with a capital P. And then throughout the body of the CC file, you can do tr and then the stream operator, a message in the standard end line, and this will, when it gets to that point, it'll behave like cout, except if you've controlled it through the option system, where say you've muted it, or you're running it through MPI, and then it will get put to a separate log file for it. In addition to the standard tr, there's tr.warning and tr.error, and there's a few more info, debug, and trace that can be controlled in different ways. But you'll see this, and it's good to use these rather than standard outs. Okay.
I think a tracer always runs the standard out, even if the level of the tracer is error.
Oh, really?
Yeah.
Oh, good to know. Okay. There is a page in the wiki for coding conventions. I'm just going to highlight two of them, just so you can get in the habit of this. To name directories, we do it in lowercase with underscore separating words. So it would be like the path to the directory name. And then inside of the directory, if you wanted to name a class, you'd have this, the class name is the name of the file, and it's .cc, and the class name is the file.hh, and then the forward header associated with it. And then when you define the class, it's this camel case where the first letter of each word is capitalized. And then function names are lowercase, and variable names have this underscore that's following it. There are other subtle rules, but for the most part, this is for the naming is what you need. White space, it's a good habit to get into is if everybody uses tabs to indent their code, then it looks good no matter what editor you open it up in. If some people are using tabs and some people using spaces or tabs after spaces, then when code gets opened up with different size tab stops in editors, it looks like a total mess. So in different editors, there's ways to specify that you want your editor just to use tabs and not spaces. And to do that, I have an example for Emacs and then for Vim and Xcode, and if you were using a different one, figure it out or ask. People who do this, it's just a little frustrating, but it's not the end of the world. So please do it correctly. Right, so the coding conventions and examples page. So tabs are these magical characters that they're just a concept of a tab, right? And so different editors can interpret that the way they want. So if you like to view yours with that looks like 3 spaces, then you can set in your editor to view the tabs as being 3 spaces. But tabs are just one tab character as a tab character. So that's the magical part about tabs. So, it's kind of a headache, but it's just a good habit to get into. If you're using Emacs, I use Emacs, I recommend it. There's an emacs.init.edl. If you copy this to in your home directory, it will set it up correctly. If anybody would like a tour of Emacs, we're going to use it for GDB tomorrow because I think it's a good way to use GDB. It's nice to use because if you can always log into a computer and it almost always has Emacs, especially on like a server or something where you don't have a graphical user environment. But other people choose Vim, and they're OK too. I don't hold it against them. But many people use Xcode as well, or something else, Sublime Text, or if you have Eclipse or something. But anyway, for your editor, figure out how to do this, how to figure out how to get it set up the way you want, because it will spend a lot of time playing with your editor. Tim put together some comments if you want to set up Vim to work with Rosetta. You should use the smart tabs in the .vimrc, the auto indent, and the syntax enable are good places to start. But perhaps other people have suggestions for packages that they like to use with Vim. And then to set up Xcode, there's right now it's in Rosetta source Xcode, Rosetta Xcode proj, but this is going to switch to Rosetta main Xcode. And then here are what you need to do to set the tabs correctly for that. This we'll talk about tomorrow, and that's it for what I have today. So if you look in this is going to be lab 2 in the that should have been emailed out. I don't know if you. Oh, that's the email lab.
Are you providing
Yeah, I'll show you what I have. So, oh, that's not it.
Every year they have a statistic of how much Rosetta, how many more lines of code there are. So we should actually shoot for more like, oh yeah, I think we should actually shoot for like Rosetta actually got smaller.
So it says to make it in your username print score. When I say to make the headers and things, you generally just go and look in other apps in apps public. I find that it's helpful to browse around and look at different parts of code for if you want to see if yours is consistent. As you look at more code, it'll become more obvious what the right thing is to do or what the consistent thing to do is. But for instance, to find the header in the preamble, it's in every CC file that you would want to open. So open one up and copy and paste it over, for instance. To figure out how to do includes